Okay, let's get started. So yeah, today we have the last machine learning and statistics lecture, and I wanted to tie up some loose ends and talk about the comparison between simulation-based inference and variational inference. I will show you a minimum example code for how to train actually with keeping, where we also look at validation loss and test loss at the end. This is something that we didn't have. And yeah, we will see how far we get. But what I wanted to start with is 2 slides about simulation-based inference, which I like to show in my talks, and they have animations, so maybe they are useful. So, but this is nothing new. This is just what I was telling you yesterday, but it's useful maybe to repeat this. So the basic idea of simulation-based, or the classic analog of simulation-based inference is approximate Bayesian computation, right? And the basic trick with approximate Bayesian computation is to do this difficult thing here on the right-hand side, estimating the posterior given some observation, by actually running a lot of forward simulations. And so this here is just the likelihood, so the simulator times the prior. And they are simply connected through Bayes' theorem, or definition of conditional probabilities, really. So the idea is to simulate a lot of data, right, by running this model. And you simulated already data yesterday. And if you ever have run a Monte Carlo simulation for collider data, this is what you were doing. Good. So now the trick is, if you want to do simulation, if you want to do approximate Bayesian computation, we need some smart data summary, something that correlates ideally with the parameter of interest. So it's enough if we can just look at individual parameters, any of the parameters that we might be interested in the simulation here. So the z here might be any of the vector components of the vector z here, or might be any function of this. If we want to measure that parameter, we need a data summary that correlates with this parameter. And in the best of all cases, it's a sufficient data summary in the sense that there is nothing else that you could learn by looking at the full data. So everything you can learn about parameter z is already part of T. And there are formal definitions of what this means, but I want to start here with the assumption, okay, let's say we have such a data summary, whether it's sufficient or almost sufficient doesn't really matter. So first step is to actually populate this plot here by running simulations. So all these green dots were produced by first picking some parameter from the prior, and then simulate, and then plug the simulation output into the data summary, and then put a little dot here. So this is how you get the green band, and then you are basically done. So next thing is, once you get an observation, let's say 0, then you just read off all the green dots that are in epsilon range and plot them here in a histogram, and then you have a posterior. And in the limit where you have an infinite number of points and let epsilon go to 0, then this will become a very smooth, nice function that is just exactly your posterior. And now the entire thing is amortized, which means if you have different observations, right? If you keep your simulation stored somewhere, you just get all the nice. I repeat the simulations for those who missed it. So the point is it's amortized. So you get any posterior instantaneously once you have a new observation. And that's a property of approximate Bayesian computation if you keep your simulations and don't just reject them. And it's also a property of simulation-based inference with neural networks. So now there are these two challenges, right? So one is getting a good data summary in the first place, and then the other is somehow taking this epsilon to 0 limit. And what I claimed yesterday, or tried to show yesterday, is that neural nets help you with both. So there are many ways to do this. We looked at neural ratio estimation, at least in the exercises, and the idea is there you take the real simulations here in red, and you have scrambled simulations here in blue, right? And we discussed how to do this. So you just take the real simulations that you have, if you have 100,000, and then you randomly mix up and shuffle parameters and observations. Then you end up with scrambled simulations. And then a network, also the network that you actually used for this ring analysis, looks like this. So there's like an embedding thing that takes the data, right? And in your case, the embedding is a CNN with 2 layers, very simple. And it spits out, I think, 2 parameters or something like this, or one. No, I think just 1 parameter in that case, not 4 like here. And then you have your parameter vector, which is also just 1 number. It's the radius, and then they are concatenated. And then you have a vector of length 2, which is plugged into a multi-layer perceptron. And then you get 1 single output. And that 1 single output will be this log ratio, right? So log ratio for posterior of, or for the posterior for your radius given the observed image divided by the prior. Say it again, sorry. No, so the S's here, they are the summaries that come out of the network. The thetas, they would be Z. Yeah, so I think half of the papers about these kind of things call the parameter theta, the other half Z. So I mix this sometimes a bit up. So this here is the parameter vector theta, which I up to now always called Z. Okay, so now here you see actually now what the network does after initialization. If you plug in, so this is like a toy model. I didn't actually write down the toy model. It's 1 parameter model that goes like, produces, I forgot actually. I think it just produces like a spectrum with 10 bins. The key point is that the parameter enters quadratically, so it's Z square, which means in the end you can get bimodal posteriors. So here you have the parameter, and if you plug in different simulations based on that parameter into this network and just plot the summaries here in that direction, you see it's not correlated, right? So these are very bad summaries, which is not a surprise because the network wasn't trained. So it can't, it's maybe a bit surprising that it's all close to 0. Could look different, but this is what the output is, so it's random. If I now start the training, and I think one can do it like this and then stop it again. So if you start the training of the network, what happens is the embedding learns a good data summary. So you see this here as the red dots. These are the, when I plug real simulations into the network, you see that something builds up, right? So this data summary becomes correlated with the parameter that we want to estimate. It's not this linear correlation like in the last plot, but it's here this quadratic function simply because the parameter enters quadratically into the model. And the blue dots are simply the scrambled simulations, so unsurprisingly, they don't build up any correlations. And then if this continues, if you continue with the training, then you see this color thing building up in the background. This is actually the multilayer perceptron that now suddenly learns to distinguish, basically it learns this ratio, right? It learns the ratio between the distribution of red dots over the distribution of blue dots. The blue dots are uniformly distributed. The red dots are distributed in this correlated way. And so this MLP simply learns their ratio. So in the white region, it's undecided. It's like 50-50. in the red region, there are more red points. In the blue region, there are more blue points. And if one continues training this, right, becomes all more contrastive, gets more contrast. And then what one can do is you can pretend we measure the specific piece of data, which maps onto this particular data summary, which changes, right, because the network is still training. But then we can read off this MLP essentially for a fixed observation at different values of the parameter in this direction here, and plot it in like a proper way. So and then you see you get a posterior. So this here is now a smooth posterior function. And it has two peaks, which makes sense because the model is built such that you have like two solutions. So it's a bimodal posterior. And what you see is the entire thing wiggles quite a bit around, right, while it's training. And then if one waits a bit, actually it settles and gets more stable. And this is the effect of learning rate decay. So initially the learning rate is quite high. It finds like a good solution. But if one wants then to have something that is stable at the end, one has to reduce the learning rate. Otherwise, the final result will be very noisy. So if you would train one step more, you would suddenly get something slightly different. You see here, here's the true value. So the posterior covers the true value in that case, and that's it. So this is a visualization of it's a visualization of how the training process works. Right, I just wanted to start with that. Are there any questions about this? Yeah.
So here for the last part of the simulation, the width, let's say, of the region didn't increase anymore, so it just oscillated and then sort of stabilized.
Yeah.
The width was, where it comes from exactly?
So the finite width here comes from the intrinsic noise of the measurement. So if I would switch off the noise completely, then this should formally shrink to a delta function. It will not. There will be all kinds of weird problems. But yeah, so if everything goes well, then this here is dominated by the measurement noise, or either by the measurement noise or by the effect of other parameters that you didn't consider, which also act as noise in that way. Yeah. No, this is again normalized to 1 by hand. Okay. Yeah. In this particular algorithm, it should it learns the normalization but not perfectly. It's approximate like everything else. So usually, when I would plot this, I would normalize this by hand to 1. Also, you see that the two posteriors should be actually exactly the same, but I think there is a tiny difference in the height. So also, the symmetry properties that you would expect will only be approximately satisfied in this setup. More questions? Yeah.
So let's see, what is the relation between the theta and the z parameters? So
theta is z. So what I called before z is here just theta.
And so the theta 1, 2, 3 are different components of z?
They would be different components of z. So in the exercise that we had yesterday, there was only one component of z, the radius. What I usually also explain when I show this slide is, let's say you have multiple parameters, so the data vector of length 4, then you could train multi-layer perceptrons. One learns the posterior for the first parameter, and then it's just the one-dimensional marginal posterior for the first parameter. Another one could learn the posterior for the second parameter. And then you might be interested for some reason into the 2D correlation between parameter 3 and 4, so you can also train a network for that. So one can, in principle, efficiently split this up. You could also train just a 4-dimensional posterior, so there's a lot of flexibility in this. If you would run a Markov chain Monte Carlo, there's no flexibility like that. You just run it for the high-dimensional parameter space. More questions? Yeah. Sorry? What it is or where it is?
What is it?
Data, I mean, let me go back to the slide. So data summary is essentially just a function of the data. So think of this like this here is an image. Let's say this is an image. In the case of this example with the rings yesterday, X was an image, right? And then the data summary is just a piece of code or like a mathematical equation that takes this high-dimensional thing and compresses it into a low-dimensional thing. So it's just a mapping from like 100,000D to 2D or 1D. And the idea of a data summary, and then this here is still a random variable, right? So if you sample random data, also t will be random. It's a function of your original data. And in principle, you can try, and then you can try to ask the question, okay, what do I learn about the parameter of interest if I don't actually look at the data, but just at the summary? And there's this notion of sufficient data summary or sufficient summary statistics, which means that everything you can learn about this parameter from data X can be actually already contained in the data summary T. So in the case, one example, one easy example is imagine you have like an observation of let's say the images from yesterday, right? So you have the rings, so you don't, somewhere in the image, you don't need most of the image to learn something about the rings. It's enough if you have the part which contains the rings. And then if you have a piece of code that actually can extract the radius directly from that image, it's enough to know the radius, right? So that would be the data summary. And often it's not so easy to get these data summaries.
Is there a systematic way to know if T is sufficient?
Not in general, as far as I know, no, unfortunately. No. Okay, the question is if there is a systematic way to know whether T is sufficient or not. So in cases where you actually have a likelihood function, you can often think about, I think there's a more general statement. So there's a group of probability distribution functions called exponential family, for which you can relate these data summaries to this core function. So it's a bit, so for specific groups of likelihood functions, if you have analytical descriptions, you can say something about what are sufficient data summaries. In general, that's very difficult. So for this example yesterday with the rings, I wouldn't know how to 100% say, okay, this is now the sufficient data summary. Yeah, that's one of the difficulties of this approach. So you can never be really 100% sure in general for arbitrary problems that whatever you have as a data summary is the best possible. And so it could be that your results are not as precise as they could be. Yep.
Is there a way to judge which components of my X are most important?
This typically requires thinking about the data, right? So it could be, if you think about gravitational waves, for instance, then often the entire, like, in time domain, then the entire signal, I mean, the entire period that you're looking at might be relevant, but then if you go to Fourier space, maybe only a few components matter. If you look at other data sets, sometimes you can clearly, like, say, just based on how data works and how the parameters affect the data, where the information sits. But this requires, thinking about how the data looks like. But usually it's possible, so it's worthwhile thinking about these kind of things. Okay, so let me go on. I wanted to show you this basic example of actually training a neural net with right, I wanted to first draw something on the blackboard. Something very obvious that we, however, didn't discuss. So again, so loss function goes down. This here would be the train loss. If this here are the number of steps that you do during training. And then there is typically the validation loss. And I claimed it tends to go up at some point again. So this is something that you would calculate. You would just evaluate the loss using validation data that you don't use for the training itself. And this tells you something about generalization of the training. So since the validation data isn't used for the network training, if the network still works on your validation data, it means that there was some generalization happening. So it could extrapolate relevant features from the training data that also apply to the validation data. And then there are all kinds of ways you could deal with that information. So one typical approach is early stopping. So you kind of keep track on when the validation data goes up again, and then you take the network weights that you had when the validation loss was minimal. Then you end up with like that network. And then if you want to actually compare now different network architectures, it's a good idea to, and you want to say something about the performance, it's a good idea to not do this based on the validation loss, but based on yet another separate data sample, which would be then the test loss. Because otherwise you bias the network that you use to the network that happens to work best on your validation data. So usually you would have 3 sets. Or if you have training data, you could split it up in 3 sets. Maybe 70% for training, and then 10% for validation, and 20% for testing, or something like this. Yep. Maybe you go first.
I've heard people say that despite everyone talking about this, that in practice, the validation loss also just tends to go down the more you train and often doesn't go back up again.
Yes, in the example that I'm going to show, that's happening. But it depends really on in practice, usually, so there are also situations where this happens. So you keep training and immediately sorry, this is the validation, so the red line. So immediately it goes bad. This can happen if you have a network architecture that can memorize noise. So that's typically, imagine you have like image data with noise, right? Then if you have a network architecture that is able to, in some sense, memorize the noise pattern, then this is nothing that is going to generalize well. And so what can happen in these cases is that suddenly the validation loss is really bad from the very start. In other cases, it just continues going down, which really depends on the specific problem. And if it continues going down, right, then I guess the stopping criterion would be a finite number of resources, finite amount of resources that you wanted to use. So in this case here, usually it helps to just use a different network architecture or resample noise during training or something like this. Okay, so this here is an example now. It's actually, sorry, I forgot your question.
You're talking about different sets of data, right? Mm-hmm. Data for training, the other for validation.
Yeah. So the idea would be you have your training or you have your data available. If you do simulation-based inference, you can just simulate your data. So you can produce as much as you want, and then you would split this up in training, validation, and some test data. And and use these separately. So here, I now wanted to just show how this might look like in a very simple example. Again, our sine curve. Now I actually use a noisy sine curve. So that's the, okay. Then, good, a noisy sine curve. You see here 100 training samples for training, 100 for validation, and I used 1,000 for testing. That's usually not the ratios you would use, but it's here useful to make the validation loss the test loss very stable. So this is the data, and then one can fit it. And right, there are lots of possible. This goes quick. So there are lots of possible activation functions that one could use. What you see here is the training, right? So the training loss goes down, the validation loss also goes down, and at the very end, we calculate the test loss here. And this is the thing one should look at when comparing network architectures. In this very, very trivial example, there's actually not much interesting happening. So the training loss goes down. It fluctuates a lot, simply because the training is using mini batching. So each time when the training loss is evaluated, actually, we look at a slightly different piece of data. So there's noise. The validation loss is pretty stable because it's always evaluated on the full validation loss. Now, that's not the result that we get, but we get this here with the ReLU activation function. So it's pretty, you see that it's piecewise linear. And right, so what I've found nice is to actually visualize now how this function is built up. And so you see this is the function here that we learned, right? And if you then look at the individual ReLUs, how they contribute to the overall function, you see this as the colored lines, right? And what you see here is that all the components, or many of the components, actually contribute, and they conspire in some sense to produce this sine curve. What you also see there, probably you can think about this intuitively or visually. It's not so easy to actually overfit with this kind of function. So I actually tried to make it overfit because I wanted to make some points about overfitting. But it turns out you can't overfit the sine curve with this kind of ReLUs. So if you would do like polynomials or whatever, I'm sure this will work. But with ReLUs, it's a bit hard. Good. And the fun thing is you can also look at different. I'll just show one other example. So let's say we take a sigmoid, actually. Right, so this should be now the sigmoid. Then it also trains. And the curve becomes pretty smooth. And yeah, you see here how the individual components from the sigmoid contribute to the overall fit. I'm not advertising to use sigmoids if you build deep neural nets. But this is just a network now with one hidden layer. So you can play around with this and get some intuition for what's actually happening under the hood and what's contributing to the function that you see here. Right. I also wanted to show you what happens when you overfit and things like this, but this didn't work. So
yeah. It looks in that plot where you just read that a lot of the sigmoids like don't do anything that is 0.
Yeah.
Would there be a way to like avoid that?
If you use the ReLU, this doesn't seem to happen. So just use ReLU. Okay, sorry. The question was, okay, in the case of sigmoids, it looks like not that many sigmoids contribute. That's true. I think that's a typical effect of sigmoids, probably, because they are pretty much localized. There are lots of other things you could use, like ELU, whatever. So there's an entire zoo of possible activation functions. So this is ELUs. They go, yeah, I forgot the definition of an ELU, but I think it doesn't stop at 0. It becomes negative and looks like a shifted exponential. So depending on what you want to do, you can, maybe different activation functions give you better performance. But the default in all the literature that you typically read about neural nets tends to be a ReLU as a starting point. Good, more questions about this? Yeah.
What's the explanation why you can't have that smooth plot for the first?
So the point is, when you have ReLUs, right, then they can only produce something piecewise linear because you sum piecewise linear functions. So you get automatically the jumps in the slope. Whereas if you use activation functions that are smooth, automatically the result is smooth. It doesn't mean that the test loss is better. Actually, the test loss looks always pretty good, no matter what activation functions you use. We usually would use ReLU, yeah, and a lot of layers. So this is not an example for how to train deep neural networks or general lessons about what works best for deep neural networks. What I want to highlight here is this way of actually getting to the test loss. That's important. And then afterwards, there's usually no way around than just try and error in many ways and see, okay, does this work better? Does that work better? Because this is a very simple network, right? It just has one hidden layer. So this will not apply to, and it works well because you just go from 1D to 1D. If you want to model something that goes from 10D to 10D, then it's a good idea to have multiple layers, and probably ReLUs will be just fine. If you train a large language model like GPT-4 or whatever, I suspect they might just use ReLU. So one doesn't know, but the default building blocks for transformer networks in PyTorch are ReLU. Good. So that's that. Then I wanted to. Are there more questions? Otherwise, I would say a bit about coverage tests. So check how to switch this off. Thanks. Good. So, right. So in general, the topic today is VI versus SBI. But also a few other things. So things that I still wanted to mention. And the first we just discussed, so minimal example with test and validation losses. the next thing was coverage tests. And that's related to the question, okay, once you train your posterior model, right, and maybe you also have a nice low test loss and so on, how can you be sure that what you see actually behaves like a posterior, like a proper Bayesian posterior? And there are no perfect answers, but I will give you the answer that is, or the approach that seems to be most used right now. And this is based on the idea of Bayesian coverage, where you coverage is a bit more frequentist concept, but you can also look at this in a Bayesian way. So the basic idea is a property that you actually would expect for any credible interval that you build. And I think I brought this down in the very first lecture. So the idea is if we estimate some posterior in whatever way, and then for a specific observation x, and we'd say it's a 1 minus alpha credible region that we base on it. So let me show this again. So let's say this is the posterior. Then you could define some region 1 minus alpha for some specific observation x, such that this region here contains 1 minus alpha % of the probability. Okay. And then the idea is, okay, if we have such a region, and then we sample random values from the posterior, then these random values should be inside that region in 1 minus alpha % of the cases. That's kind of automatically true, because that's the way we build the region, right? So automatically, if 68% of the mass sit in this region, then also 68% of the samples should be in the region. Okay, and for Bayesian credible regions, we would now, or for a family of Bayesian credible regions, we would now expect that this holds individually for every observation. No matter what you observe, you would expect this property to be true, okay? So now what we could try to do is, okay, instead of building these regions now from the true posterior, which we don't know, we build these regions based on our approximate posterior on this function Q, okay? So let me write this here. Yeah, so I write it again. So we would still have here the samples from the true posterior, which would be actually tricky to obtain. But now we would check whether those are contained in the region that we built based on our fitting function. Okay. So these are the regions that you had yesterday when you were running the code. At some point, you got this banana-shaped posteriors, right? Or banana-shaped credible regions. So now we call this here alpha hat because it's not automatically alpha, right? So what we now could hope is that, okay, but now we could use this here as a test, right? So we have the regions. We test how often the actual sample from our posterior falls into that region. The only problem is that we can't sample from our posterior in the first place. So we can't do this test individually for any observation, but what we can do is the trick that we played before. We average this now over observations. And then instead of sampling first an observation and then something from the posterior, we sample simply first the parameter and then an observation, right? So that's the same trick we used to actually get started with simulation-based inference in the first place. So now this statement here, this is a quantity that is averaged over x rather than something for a specific value of x. But what we now could check is whether, at least on average, this coverage is true. So whether on average this here equals the nominal value. So that that I used when generating the interval. Okay, so essentially we ask the question, okay, if we generate these intervals based on our fitted network, and then evaluate the interval for many simulations, so for many parameter data pairs, how often is my parameter actually included in the 68% credible region? How often is it included in the 95 region, right? So you could imagine you have a data point. You played this yesterday probably, right? So you have a data point here, and then is it included or not? And then you rerun the code, and then you have another posterior which might be here. True data point is here, something like this. You just count the number of occurrences of, okay, it's within 1 sigma, it's with 2 sigma, and so on. And then what you can do is you can make a plot, which kind of looks like this. So on that side we have the nominal. On this side the nominal coverage or credibility level. And on that side we have the actual coverage. Ideally now I write the diagram. So let's say this year is 68, this year is 95% credibility. Then if we run many simulations and just count the frequency of cases in which the two parameters contained in the 68% credible region, we might end up exactly here, which would be nice. So this would be 68, but we might also end up a bit higher. That would mean that our region contains the true value more often than we claimed when building the interval. Same for 95. So that would be the situation where the curve looks like this. Could also be that and this usually happens when you overfit the entire problem. It could also be that the intervals are too good, so that they are too narrow. And if you repeat the experiment many times, it turns out that most of the time, or more often than it should happen, the true value is outside of the 68% credible region. So this here would be, it's sometimes called overconfident intervals. And this here would be called, let's say, conservative. Conservative sounds positive, but what it also means is, I mean, it's still wrong, right? So, so ideally, you are here on this diagonal line. And for neural ratio estimation, at least, okay. So what you typically observe is that initially, when you train the network, you start somewhere here. If you keep training, it goes at some point to this diagonal, more or less. And then if you keep training further and overfit, especially when you see the validation loss going on up, then typically this is reflected in this type of plot as overconfidence. But this doesn't mean this is, so you can also have something where you do early stopping and everything looks nice, and then you look at the plot and it doesn't look good. Even if this plot looks good, it doesn't mean you have the most accurate posterior. It doesn't say you anything about the data summary. So even one fun thing is if you do this test for the prior rather than for the posterior, it would be just on the diagonal. So this just wouldn't tell you much. Nevertheless, so that's a typical test. Again, it's not a test that everything is really fully Bayesian, but it's like a tractable test that is reasonably easy to do, and it's kind of a sanity check for things going right. Other questions about that? Yeah.
When you average over observations, you get a situation where you just severely undercover for some observations.
Yeah. So that definitely can occur. So that's also one of the concerns with this in general. So if you have like a gigantic parameter space with very different observations, and you train a neural net to estimate the posterior for all of that, and then afterwards the only test that you can really make is a test like this, that doesn't mean that the network shows the same performance everywhere. And in fact, I mean, you can afterwards, when you have this, right, generate training data just from subsets of the parameter space and look at these plots, and then you often see, okay, in half of the parameter space you undercover, and the other half you overcover, or things like this. So that can happen. But it's very difficult to do the test exactly, because for this you actually need samples from the true posterior. So the hope is a bit that if you shrink the parameter space and focus on a specific observation, this here becomes less severe, but it can be a problem. Yeah. Yeah.
Let's say I take the 95% level.
Yeah.
And the alpha hat is what our estimate. I mean, it's our
Yeah. So this here is the value that we use for defining the interval, for saying, okay, now that I call the 68% credible interval. And the alpha hat is the thing that we get by running MC, or not MC. So yeah, for doing Monte Carlo estimates of the coverage, by actually just checking for many simulations how often the true value is inside that interval, which I called 68%, 68% credible interval based on Q.
So alpha is what you choose.
Alpha is what you choose. Alpha hat is what comes out of Monte Carlo. Yeah, so there's more to say about these kind of tests, and there are also other suggestions in the literature what one can do to test SBI results, but that's like the most common that you see in like every paper. And yeah, typically you wouldn't plot this necessarily as 68 or 95, but you see here just directly 1 minus alpha, so p-values. Good, so let me check. I don't see. Let me just check. Right, so next thing that I wanted to discuss is sequential simulation-based inference, I think. No, failure modes. That's more important. Good, so one interesting thing is now the following. So So both techniques, variational inference and simulation-based inference, if everything works perfectly, they solve the same problem and you get the same answer. So that's not our concern, but it's interesting to ask the question: what happens if things go wrong, and how would they typically go wrong? And this is related to the KL divergence. So this is now more related to neural posterior estimation and variational inference. So neural ratio estimation might behave a bit differently, but it's useful to look at the KL divergence. So let's suppose we again have the KL divergence from A to B now. I call this A and B so that we don't have to tie this directly to what is the posterior and what's the variational function. And I'm just writing down the definition again. So log ratio of A divided by B, right? And what we see from this is, or the general statement that one can make is that if the KL divergence is finite, right, that means that wherever A is larger than 0, also B has to be larger than 0, okay? Otherwise, you get a logarithmic divergence. And the reason is simply think about A being non-zero, right? And A not being non-zero, if B goes to 0, you get a logarithmic divergence. And that's certainly not something you would be able to tolerate if you use this as a loss function. So if you use KL divergence as a loss, typically whatever you get in the end of the day after you do the fit is a situation where this condition is satisfied, okay? And this has practical examples, so or practical consequences. So let me give you a very simple example where the true function that we want to fit is bimodal. So it has 2 peaks, but we decide to only fit this with Gaussian. Okay, so with a function that has 1 peak. Then we can have 2 situations. So one is we look at forward KL divergence. This was the situation where we had dKL from P to Q. This was the starting point for neuroposterior estimation for simulation-based inference. And in that case, what one would expect to happen, let's say, where do I have red? So the posterior is this red function with two peaks. And the variational function that we fit is blue. Then we have to make sure that wherever P is non-zero, also Q is non-zero. So the typical outcome of a fit would look like this. Okay, and one way, so yeah, forward KL is mask covering typically. So what you see is that if you use the wrong or some function that is not flexible enough to actually accommodate the full complexity of the posterior that you have at hand, then a tendency of simulation-based inference, or at least of neuroposterior estimation, would be to try to cover everything that is non-zero. So a consequence is that you also include parameter values now in your posterior, which were clearly actually excluded by the data. But at least you don't exclude stuff that is still allowed. Okay. So this would be the typical failure mode of forward KL divergence. If we now look at reverse KL, which was the starting point for elbow maximization, the situation is exactly the other way around. So we would have, again, our bimodal posterior, but now it's on that side. And now if we do a fit, typically what would happen is that that Q will pick some of the two modes. So let's say this one here, and just get attached to that. Okay, and the reason is simply that wherever Q is non-zero, also P has to be non-zero, but that means it can't stretch from one mode to the other. Okay, so that's why reverse KL is called, or let's say variation inference, in general, what's called mode seeking. So what this does is VI is very efficient in finding a good fit to the data, but it might not find all the parameter space that gives a good fit to the data. So in this case here, you would have the tendency to exclude parts of the parameter space that are actually not excluded. If your true posterior is actually just a Gaussian, right, this doesn't matter. But if it has more complexity than you can accommodate in your variational posterior, then there can be problems. And actually, if you think then about elbow maximization, right, having the peak here or having the variational posterior here, or here would just correspond to two local maxima in the elbow. So you would have two local elbow maxima. And again, that's not, so if you think about the classical analog, which is chi-square fits, if you would be in a situation where there are two different parameter ranges that give a good fit to the data, also if you just minimize chi-square, you could end up in one or the other minimum. So you get the same effect here and so on. Okay, so this is useful to know because, yeah. Yeah, you could do that, but that's not guaranteeing you that you actually find all the modes or that you find them in any statistically meaningful way. I think Sorry. The question was, okay, now the nice thing with VI is at least you don't get these very wide posterior, I guess, but you resolve individual modes well. So why not just running the thing multiple times and then maybe you recover the modes? Yeah, you could do this, or you could have a mixture model, right, where you have multiple peaks in your posterior, or multiple, just a sum of multiple Gaussians. Maybe they pick this up. In practice, it turns out that it's not so easy to run this in a stable way, so that results tend to depend on initial conditions, like it would be in any minimization problem where you have like a complex loss surface. There's also Yes, definitely. I mean, you can, if you have a normalizing flow, what it could do is it could just split this one peak. You could start with something like this and then split it up. And in general, that's always possible. But there is in general also the tendency that if your model is undercomplex, with reverse KL, you will typically underpredict uncertainties. Whereas with this here, SBI, you will typically overpredict uncertainties. So it's like it's like approaching the true posterior in one case like from inside out, and in the other case from the outside in.
Similar question, like you cannot add like the small values for the distributions such that not having these problems, or I have a limit for the divergence.
But
what I mean is the divergence. I have like a small limit for that, or a large limit for that.
I'm not sure. So how would this help?
Yeah, I was just thinking that instead of having 0, I should just add like my hand like a small.
You mean to the loss function itself?
Yeah, like not to reach the 0.
But I think this wouldn't help here. I wouldn't see how this helps.
Because the problem is not that like you have 0 in the logarithm.
Yeah. This is what you mean. Okay. Okay, I should add. This is a general problem of KL divergence. But there are quite a few variations of these algorithms that are based on other divergences. So there's an entire family of divergences called F divergences. KL divergence is one version of them. You can start with another divergence and get similar algorithms which have other failure modes. I can't like give general statements now. I will talk about one alternative maybe a bit later when I talk about another aspect of the story. But this is something that one actually observes. And so when I started with ML for astrophysical data analysis a couple of years ago, I only did VI initially. And for these kind of reasons, I stopped doing it mostly. That doesn't mean it's a bad thing, right? So if you want to actually have a good fit to the data and have a model that actually describes very well your data, but you are not concerned too much about excluding parameter space that is also there, then VI works great, right? And it has other benefits, like the ability to also have degrees of freedom in your simulation model and optimize them directly. Good, so that's one aspect. There's another side to the story which is related, and this is marginal. Yeah, I'm now at 4. So what we now can do is we can look in some sense at the same problem, but in a more high-dimensional perspective. And this is like, let's say we have a posterior that we want to fit, right? So our fitting function. And it's a high-dimensional parameter space. And let's say our posterior can have high complexity, right? So it can fit anything to some extent, but we decide to factorize it. So we decide to write it as a product of posteriors for each. And I'm not writing the x here, but it's not too critical. So we write this as a product of individual distributions. Okay, so in the context of variational inference, this is called mean field approximation. And what this essentially does is, okay, you say, so one way this occurs is you model your variational posterior as a Gaussian, as a multivariate Gaussian, and then you say your covariance matrix is diagonal. That's something that you can do. And sometimes you want to do it because then you can deal with million-dimensional problems and everything. I mean, things become feasible. But the price to pay is that you assume that your posterior looks like this. It's factorized. Good. So now we can use this as a starting point both for variational inference and for simulation-based inference, and we will get two different answers for what these individual terms or factors will actually turn into. If you use simulation-based inference, what happens is that, and you can see this by just taking the loss function, plugging this in here as a variational posterior, and then realizing that the log of this, right, will just turn into the sum of the log of all these individual factors. And so you get basically a problem where you start optimizing where you start learning the posterior for each parameter individually. And what happens is, in that case, all the posteriors, all these factors will start to fit the marginal posterior for this one parameter. Let me remind you that marginal posterior means, and I'm writing this now like that this is formally given by the full joint posterior, but integrated over all parameters except, in this case, the first one. So the -1 means it's all parameters except the first. Okay, and that's a nice property because this means for the individual measurements that you here performed, you actually get realistic uncertainties, right? You marginalized here over all the rest, like implicitly, taking into account parameter correlations correctly and so on and so forth. So if instead you use VI, so forward KL, no, sorry, reverse KL, what happens, and you can find more details in the lecture notes, is I will just write the equation. So what this turns into is a more complicated expression. So this here is the average over all parameters but the first one, and then the log of the conditional posteriors. So this here would be, again, all the other parameters. So in the case of VI, actually, you don't get the posterior, but you get something that is kind of a weird mixture of conditional posteriors. I will draw a picture in a second, but in general, these conditional posteriors are more narrow than the marginal posteriors because you pretend you know some of the other parameters. So in that case, you would, in general, get two strong constraints. So and I can draw this in 2D. So let's say we have here Z1, and we have Z2. And let's say the true posterior might have like might be whatever, banana-shaped. Then what you would get if you do VI is you might get some posterior that sits here, okay? So let me remind you, so conditional, so posterior for Z1, which you conditioned on a specific value of Z2, would just have typically this width here, right? Because you pretend you know Z2, then you would also know Z1 within this small range. So in general, with VI, you would end up with a posterior that would be like somewhat, I mean, completely underestimating the true posterior. And it looks, again, like it's approximating the truth from the inside, right, from the inside out. Whereas with SBI, if you would do this, and it's a circle here or ellipse simply because we factorized it, right? So that's the reason why I draw it circular. Whereas with SBI, if you would just multiply the Q for Z1 and Q for Z2 and then draw a posterior, again, we wouldn't have any correlations, but we would get some large circle, which would correspond to simply project. I mean, this comes from the Q's approximating the true marginal posteriors property. So in this case, you would overestimate the uncertainties in some sense, but you anyway only looked at the marginals. So this is a quite different. I mean, this has profound consequences, right? So what this means is if you actually want to use VI for studying very high-dimensional problems, you need to make sure that you also model all the correlations between all the parameters properly. Otherwise, you might, or you will, eventually underestimate parameters. Now, that's a very known property of VI, and there are papers in the literature which explore then different loss functions, which help to make that problem less severe. But
the top equation is the pi there reduced. You wrote a proper thing. It looks like you wrote each term of the product. The dot dot. Is that right? I don't see I appearing anywhere.
Sorry. Yeah. Okay. Yeah. It's just the product, right?
Okay.
Yeah. Sorry for that. Yeah.
Can you comment on how this is related to other notions of mean field theory, or is it a misnomer?
I don't think it's a misnomer. It's just a different community. But I couldn't really. I haven't thought about. It's on my to-do list to think carefully about the connection. I guess there will be connections when you start describing statistical systems with mean field theory to that. But yeah, I don't have deep opinions about that. Good. And in the context of SBI, also one wouldn't call this mean field theory or mean field approach. I think it doesn't exist there. But I wanted to highlight this aspect here. Good. So what we learn is that if you use variational inference, you have to be careful that you model all the correlations for all the parameters correctly in order to get realistic uncertainty estimates. In the case of SBI, you can also focus on individual parameters and get realistic answers for them individually. Good. There's one last topic I wanted to cover, which is sequential inference. Okay, so 5. Okay, so one nice aspect of approximate Bayesian computation and also SBI is this amortization property, right? So the fact that after you trained a network, in principle, you can apply it to any data, and you will immediately get the posterior. But that's at the same time also occurs, and if you're in a situation where you actually just have a very complex piece of data, but just one, right? And you want to analyze it very well, because if you use SBI, you in principle have to first train a network that solves all possible inference problems before you actually apply it to the one problem that you have. And sometimes that's not bad, right? So sometimes you actually have a stream of data that comes in and you want to analyze it quickly, then this works. But there might be the situation where you just have, let's say, one piece of astrophysical observation, and you want to analyze it carefully, and then it becomes difficult. So let's suppose this is our prior space now, okay? So it's a huge prior space, and let's suppose that the posterior actually sits somewhere here. So it's, if you would estimate the true posterior, it would be like a little circle over here. What this means is that basically most of the training data that we got far away from that region which has a high likelihood, right? So that region where the simulations are similar to the data, most of this is completely irrelevant to get a good answer in this region here. So actually only maybe simulations this doesn't work. Only simulations maybe in this region of the parameter space are informative if you want to say something about the underlying posterior. And this here would be the full posterior range, and this here would be the relevant range. And I'm not really saying here what relevant means in that context, but loosely speaking, it just means that these are the parameters which could have likely led to this observation, whereas the rest is very excluded by the actual observation that you have. Okay, so now this has two disadvantages. So first, it's quite wasteful in terms of running simulations. So I'm just writing. It's wasteful in terms of running simulations because you run most of them for no good. And at the same time, it also makes the job harder. For the neural network that you want to train, right? Because the neural network has now to have enough capacity to actually be able to solve any possible problem. You have to be able to learn a good summary statistic for all aspects of the parameter space, and so on and so forth. So for these reasons, it tends to be quite inefficient. Right. So the trick is now, or the idea of sequential simulation-based inference is now to focus systematically on the region of the parameter space that is most relevant. And there are quite a few ways to do this. I sketch here the most basic idea, or the most basic algorithm. So focus training training simulations that you run, so training data sequentially on some specific observation, okay? And one way to do this, and it's not necessarily the best way, but it's maybe the simplest way, is you initialize some initial proposal distribution when you generate training data, right? So again, so data always is generated by your simulation model, usually then times some prior, right? But now the idea is to replace this prior by something that isn't the prior anymore, but that can focus on the relevant parameter space. So you're essentially changing the prior for your problem, which of course can cause problems, which you then have to undo. But that's the starting point. So initially we would use as the prior, or as the proposal distribution for the simulations, we would use the actual prior. So we would get simulations all over the place. And then in multiple rounds, what we would do is we sample. We generate training data by sampling, or sample from the likelihood and the proposal. So we run our simulation model for points that are drawn from the proposal distribution, parameter points from the proposal distribution. Then we train somehow a network for the posterior. And here we have to be careful because we want to have the posterior assuming the correct prior. So one has to, there are different tricks one can play to make sure that for this posterior we don't use the proposal as a prior, but the actual prior as the prior. And the easiest would be to just divide by the proposal and then multiply by the prior. And then as a next step, we just set as a new proposal the just learned posterior. So we use the posterior that we get from the first network training as proposal distribution for the next training. And we iterate a few times. And in the process, at the very end, the training data will be actually drawn from the posterior itself. And necessarily be very focused on the relevant parameter space. So this could then look like the following. Yeah, I can just sketch this. No, because we have 5 minutes, let me show you some slides which visualize this. Okay, that works. Right, so here you see whatever. So these are these coverage plots. Good. So here you see an example for this with specific training data. So this here are strong lensing images. Oh, not really strong. I mean, these are simulated strong lensing images. Imagine you have like a background galaxy and a foreground galaxy, and the light from the background galaxy gets lensed, right? And this can turn into these patterns. The foreground galaxy is not shown in these images because it's just an example, right? Good. And now let's suppose this is now training data. I forgot the number of parameters, but it's about 10 or something describing where the background galaxy is, what's the mass of the foreground galaxy, what's the mass distribution of the foreground galaxy, all kinds of things. If you randomly draw from reasonable priors, these are all kinds of configurations that you can get, right? Now let's imagine we train a network to tell us, so and one of the parameters you have in describing these images is what's called the Einstein radius, which tells you something about essentially the mass of the lens, okay? And let's suppose we want to measure this one parameter now. If you train a neural net now on images like this here and plot the posterior, we will get an answer, right? So the neural net will learn the data summary. The data summary gets correlated with the parameter, and we get a posterior. In order to make sure, and in the limit of infinite training data and infinite flexible network, it would be the true posterior, right? But what we get is something. This blue curve, let's say. And this is the target observation, right? So the target observation looks very specific, looks like this. So if instead now we would have training data that is much more focused on the parameters that are compatible with the target data. And the easiest way is to just like, shrink the prior, right? So cut away parameter space that is not allowed. I haven't said how. But let's imagine we do it. Then the training data suddenly looks like this, right? So you see it still varies, but all these images are very similar to that image. Now, if you train a network on this here, on these training observations, and then let it generate a posterior, let's say with the same network that we used here, and with the same number of simulations that we used in both cases, what will in general happen is that the posterior is more narrow, okay? And so, and again, in the limit of a large number of simulations and high network capacity, we would expect the correct posterior here. But if we do it in this targeted way, in general, we can get away with much like less complex networks and much less training data. So the general idea is now to figure out a way how to start here and get here. And the idea that I just described works like you first train a net based on this training data. You get this posterior. You then use somehow this posterior to generate new training data, which eventually might look like this. And then you end up with the final answer. And there's another slide which shows how this can work in multiple rounds. I'm not sure why this doesn't move. It should. Yeah. Good. So you can, that's the target. Then you might train the first network on training data like this. Then you see here the range, the parameter range for the Einstein radius. So initially, it's from 1 to 2. Then in the next round, it's a bit smaller already, because from this training data, we could, based on that training data, we could exclude this region of the parameter space. Same is true for all the other parameters. No, it's actually 25 parameters. So a lot of parameters. So for all the parameters, we played this game and we removed parameter space. And then in the next round, you get less variance, and so on and so on and so forth. And in the end, the variance is, of the training data is quite small. And we get answers for things like the Einstein radius that are compatible with what you would expect if you would just have run a Markov chain Monte Carlo in 25D. Yeah.
How do you know you're not, I guess, like mode seeking within the parameter space?
Yeah, so that's in principle, so there are ways this can fail, but usually the problem is not the modes, because modes don't really in that form exist in SBI, so it works very different. So the idea that there's something that peaks multiple times doesn't occur. It's more like, if you remember this plot where we had the two modes in the posterior with the quadratic test statistic. So the summary statistic. This is how modes typically show up in SBI. So where do I want to get with this? So, okay, one aspect is that if you think about a high-dimensional parameter space with many modes, right, and let's say 10D, if you look now at low-dimensional projections, marginal projections of that parameter space, then often all these modes get mixed up and turn into something that is unimodal. So often from an SBI perspective, the problem can be much simpler than what it looks like if you try to estimate all the parameters at once. But there are cases, so for instance, if you have resonances or whatever in your predictions, then it can be difficult for SBI to actually find the relevant parameter space. We can talk about this after the break a bit more. I can give you some examples. Good, so just 30 seconds. Just want to show how this can look like. So this might be the initial parameter space, and then one can, so the way we tend to do this is not to actually use the posterior estimate from a previous round, but we like just truncate the prior. So we keep the prior, but we kind of cut away parameter space that is clearly excluded, and then inside what we didn't cut away, we still keep the prior, then we don't have to correct for anything. That's easier. And you can see this here visualized. So initially samples might be from this large parameter space, the true posterior might be here, and then sequentially one can zoom in. And this is kind of stuff that works in practice. So if you then do this for gravitational waves, for instance, then initially the posterior for here, the chirp mass might be white, and then in multiple rounds it shrinks to the correct answer. Good, so this was the last point that I wanted to make. Yeah, so I'm done for now. And then we will have in 30 minutes the last tutorial where I can talk a bit more about this. And we can keep going through the examples that you already have. Okay, thanks.